The purpose of the iodimetric titration is to calculate the strength of a reducing agent, and normally we use thiosulfate ion, tin ion, sulfide ion, arsenic ion or antimony ion as reducing agent. Iodine acts as a mild oxidizing agent in solution according to this reaction. Iodine gains 2 electrons, gets converted to iodide ion. We have to use iodine in this titration, but the problem is that this iodine is not soluble in water. Iodine is non-polar. Iodine atom, another iodine atom. So it is non-polar. However, water is polar. And the rule is polar dissolves polar, non-polar dissolves non-polar. So that's why iodine being non-polar is not soluble in water. So what we do? We have to prepare a solution of iodine. For that, we add little amount of potassium iodide. When we add potassium iodide, then iodine gets converted to Ki3, and Ki3 is soluble in water because it is polar. And still iodine is available because this reaction is actually reversible reaction. So Ki3 will give you iodine. Whenever iodine is consumed, this iodine will be produced again by Ki3. Iodine is first mixed with sodium starch glycolate to have blue colored solution. This iodine which we have in the form of Ki3 in the water solution, we have to mix sodium starch glycolate first so that we can have blue color. This blue color will disappear later on and we will say that endpoint has reached. Then other reactant, for example sodium thiosulfate, is mixed in small steps. When iodine dissolved in solution is used up, there is no iodine, by sodium thiosulfate the blue color disappears at the end point, and that signals the end of the reaction, and we can calculate the amount of iodine used and hence the sodium thiosulfate used. How we do that I will explain through steps. First, understand the reaction. Iodine reacts with thiosulfate ion. Similar reactions will take place with other reducing agents I talked about. So for example, tin, sulfide, arsenic, antimony ions also similar reactions will be there. Here iodine we have known standard solution. So we already know the amount of iodine and then we calculate the amount of thiosulfate ion used. So on that basis we calculate the amount of thiosulfate ion used. For other reducing agents, the reactions are, for example tin, this will be the reaction, I2 plus SN2 plus will give you SN4 plus and we will get iodide ion. With sulfide ions we will get sulfur and iodide ion. With As3 plus ion we will get As5 plus ion and iodide ion. With Sb3 plus ion we will get Sb5 plus ion and iodide ion. These titrations in which iodine is directly titrated against a reducing agent are called iodimetric titration. And this word is important, this keyword, that in this case in iodimetric titrations iodine is directly titrated with the reducing agent. Steps involved in iodimetric titrations. This is the most important part of this topic. Take a standard solution which is of known concentration of iodine in the iodine flask. So in iodine flask we have the known concentration of iodine. Obviously we need to dissolve it in Ki so that it is dissolved in the water. Add 1 ml of indicator, that is a starch or sodium starch glycolate in the flask, and that will result in blue color. So now you will have the blue color in the flask. Take the solution of reducing agent, for example sodium thiosulfate, which is called analyte. Analyte means that substance which is to be analyzed. We don't know the amount of this one. We need to know the amount of this particular substance, that is called analyte. Here in this case sodium thiosulfate, it can be any other reducing agent we have talked about. Out of those, any reducing agent. Now we add this analyte drop by drop in the flask. So in the burette we have the analyte, we add the analyte drop by drop into the iodine flask. So what will happen? This analyte will react with the iodine as per the reaction I have already talked about. This is the reaction I talked about. This reaction will take place when analyte is mixed with iodine solution drop by drop. And the blue color here will stay because not all iodine is used up. So initially the blue color will stay in the iodine flask, and the reason is that we have sufficient amount of iodine. But once all iodine is used up, then the blue color will disappear because now we don't have iodine. Iodine with starch gives us blue color. When all of the iodine is used up, then even if a starch is there, blue color will not be there. That will indicate the end point because the solution will become colorless. Means all of the iodine has been used. Now we know the amount of iodine which was present in the flask. From that, obviously, we have to calculate the concentration of sodium thiosulfate. How we do that, I will be talking about it. This is the reaction which happened when we mixed sodium thiosulfate into the flask. We note down the quantity of I2 used. From amount of I2 used, we can calculate the amount of S2O3 2-, that is thiosulfate ion used. Now, how do you calculate the strength or molarity of sodium thiosulfate reducing agent in the burette? And that is something most of the books and videos have not talked about. Answer is very simple. For example, if you got the 60 milliliter of sodium thiosulfate, this can be any amount, okay? I'm just taking an example of 60 milliliter. How do you get that amount? You get that amount by the decrease in the level of burette. So initially in the burette, if you had 200 ml and then the moment endpoint reached, you had 140 ml, it means 60 ml used. And suppose the amount dissolved in the 60 ml of Na2S2O3 was 5 gram. Then number of moles of Na2S2O3 will be its mass used divided by its molar mass. I'm just going back to explain it through the diagram. In the diagram, if you see here, we know the known amount of iodine. So suppose 1 mole of iodine used. Suppose we had 1 mole of iodine here. Okay. With this 1 mole, the amount of Na2S2O3 used can be calculated with the help of this reaction. 1 mole of iodine will react with 2 moles of thiosulfate ion. If it is sodium thiosulfate, 2 moles of sodium thiosulfate. So if we already know that we had 1 molar solution, it means there was 1 mole present in 1 liter. Then when the end point is reached, 2 moles of sodium thiosulfate would have been used. So from here I will get the amount of S2O3 2- or Na2S2O3 used. So when we get the number of moles directly, or you can calculate grams also, can convert it into molarity by the equation number of moles equals to mass divided by molar mass. Once you have the number of moles, you can calculate the molarity. Molarity will be number of moles divided by volume of the solution in liters. So in this case, number of moles 5 by 158. 158 is molar mass of sodium thiosulfate divided by the volume in liters. It is 60 ml, so I have converted it into liters. Once you solve it, you will get the molarity of the sodium thiosulfate reducing agent. Understand this flow diagram for iodimetric titration. What we do? First, we take standard solution of iodine and we add indicator into it. Here obviously when we take solution, we will have to add Ki just because iodine is not soluble directly in the water. For that we add Ki, then it makes the iodine soluble in water. We get blue color in the flask. After that we add analyte drop by drop into this flask. This reaction takes place. Blue color disappears when all of the iodine is consumed. By what? By sodium thiosulfate. We get the amount of iodine consumed. We already know how much amount was present in the flask. That is known quantity. From that we get the amount of reducing agent, for example sodium thiosulfate consumed. How do we get? By the reaction between iodine and sodium thiosulfate. After that we calculate the molarity, that is the strength of sodium thiosulfate using mass and volume consumed to reach the endpoint.